Hello, my name is Heidi and this is my video for the photovoltaic lamp project development of the analysis of electrical circuits class. So first of all, for the introduction, basically photovoltaic or PV systems convert sunlight directly into electricity. We characterized first the PV module. We measured open circuit voltage, short circuit current, and IV and PV curves. This measurement let us see how the cell behaves and irradiance changes, and they informed our biasing choices for the transistors in the lamp circuit. In Mexico, and for a little bit of context, solar PV is growing rapidly. In 2024, installed capacity is around 12 and 12.5 gigawatts, and solar is trending to about 8% of national generation, up roughly 6.2% in 2023. This reinforces the relevance on hands-on PV applications like our lamp, for example. For the theoretical development, our circuit uses a diode, resistors, a BJT, and NMOS transistor. Basically, the control logic is pretty simple. During the daylight, high PV voltage keeps the transistor cut off, so the LED is off. And at night, the PV voltage drops, and the transistor conduct and the LED turns on. This behavior implements an automatic solar lamp without the need of a microcontroller. Here we show the theoretical systemic along our practical build. Basically, the systemic guided our component selection and connections, and then we translated this into a breadboard layout, verifying polarities, transistor inputs, and LED orientation. Later on, we assembled and tested the system. With the PV cell covered under room light, LED stayed off as expected, and as shown in this picture. And when we covered the PV cell to simulate night, as shown on this other picture, the LED turned on. This direct day-night total validated both our biasing and the control path through the diode, BGT, and NMOS. For the measurement results, we recorded voltage measurements and current measurements at keynotes and components of the PV cell output across the LED and the BGT and NMOS. This measurement confirmed the intended operating regions. Higher PV voltage pushes the transistor towards cutoff during the day, and reduced PV voltage moves them into conducting at light, supplying the LED. And collecting both voltage and current gave us a complete picture of the circuit state in each condition. For my individual conclusion, personally, this project helped me connect theory and practice. Building the circuit after analyzing the IV and PV characteristics helped us as a team to see how device model translate into real-world behavior. And basically, the day-night test made the control logic tangible, and the measurements reinforced again why characterization matters before picking operation points and thresholds. This is the list of our references used, and thank you very much.